Thanks, Fred. Yep, thanks everyone for being here, and yeah, thanks to the organizers for having me. All right, so parts of what I will say is based on joint work with a whole bunch of people, some of whom are here. And so I want to talk about average case statistical problems, kind of in high generality, but for concreteness, it helps to fix one particular kind of running example. So let's talk about the planted clique problem. So planted clique problem means I'm going to think about two different distributions over random graphs. The first one is just gn1/2, so a totally random graph, n vertices, each edge occurs probability half. And then we have the planted clique distribution, where you take first a random graph, then you pick k of the existing vertices chosen uniformly at random, and I plant a clique there, meaning I connect them all to each other. And we're kind of thinking of this clique as the hidden signal that we want to recover. Now, in this model, there's a few different algorithmic questions we might ask ourselves. So the first one is maybe the simplest, which is just detection. So can you distinguish these two? Either I give you a graph with a planted clique or without. Your job is to decide which one it is with high probability. High probability meaning probability that tends to 1 as the size of the graph n goes to infinity. But also, we can talk about the recovery problem. In recovery, I'm going to guarantee you that there is actually a planted clique. So the input is drawn from distribution P. And your job is to actually find the clique. Let's say exact recovery, although it doesn't really matter so much. All right, and then the third one is maybe slightly more obscure, which is the refutation task. So this won't play a huge role in the talk. If you choose to ignore everything I say about refutation, that would be OK. But I wanted to include it because I know some people do care about this. So refutation is a question of now, given a graph that's not having, it won't have a planted clique, can we algorithmically prove to ourselves that there's not a clique? Perhaps by using some kind of proof system like sum of squares or some kind of convex relaxation. And so formally speaking, here's how the refutation task would be defined. So your algorithm is supposed to take in a graph. It's supposed to output either no or maybe. And no means no, there is not a clique. There's not a k clique in this graph, and I'm absolutely sure of it. And maybe means I don't know, I give up. Right? And to succeed, you have to have these two properties. So if there actually is a k clique, you have to say maybe. Or in other words, you're only allowed to say no if you're absolutely sure. But if I give you just a random graph, you are going to successfully say no, right? You're going to successfully refute with high probability. OK, so are these three tasks clear? And so just to recap, the situation for a planted clique is that all of these have polytime algorithms when k is bigger than root n. These algorithms are based on the adjacency matrix and looking at its leading eigenvectors, eigenvalues, things like this. We don't know polytime algorithms when k is smaller than this, even though information theoretically you only need k to be like log n if you want to do some kind of brute force search. Right, so the main question here is this inherent? Do polytime algorithms actually exist, or do they not? And can we prove it or say anything about this? So it turns out for planted clique that all these three have the same threshold of root n. I don't want to give the impression that all three of these tasks are equivalent, because this is not true in general. It's kind of a coincidence that it happens for planted clique. So really, more generally speaking, you should think of the three problems being arranged kind of by this picture, where the arrow means if I could do this problem, then I could do this problem. So detection is formally easier than the other two. And there really are plenty of problems where these thresholds can all be different and so on. All right, so what are we going to do? Average case complexity theory is kind of notoriously difficult. We can't really prove outright that these problems are hard. But we'd like to have some way of arguing that these problems are hard so that we know when to stop looking for better algorithms or to direct our efforts to problems that are likely to have better algorithms. And so here's this framework that's I think growing in popularity, which is to study a restricted class of algorithms, namely these low-degree polynomial algorithms. So what do I mean by this? I'm talking about an algorithm that itself can be represented as a multivariate polynomial whose inputs are all the entries of my adjacency matrix. Right, so I observe this graph. I have like one input variable for each potential edge. It's either a 0 or 1 saying, is the edge there or not? And you're allowed to take any polynomial of those edge variables and output a number. And OK, what kinds of things can you do with this? You know, for example, I could count the total edges in the graph by adding up all my inputs. I could also count the total number of triangles using this degree 3 polynomial. In some cases, maybe I have one distinguished vertex. Like if I'm trying to decide, is vertex 1 part of the clique, I could do something like look at its degree or count the triangles that contain it. You can also do some sort of spectral things, at least approximately. So a trace of a high power of the matrix, you know, gives you some approximation of the largest eigenvalue. And so heuristically speaking, we kind of think of this degree D. So this clicker is working sometimes, but mostly not. But this degree D is thought of as some kind of proxy for the complexity of the algorithm, or which we heuristically think of being as related to the runtime. So you know, loosely speaking, you can think of polynomial time algorithms as kind of being sandwiched in between constant degree polynomials and logarithmic degree polynomials, in the sense that, you know, if you have a constant degree polynomial, it has like n to the d terms, and so you could compute that in polynomial time. And you know, the other side is even more loose, but the claim here is just that lots of important algorithms, lots of important polytime algorithms, like things like spectral methods, approximate message passing, and so on, turn out you can capture them, implement them using logarithmic degree polynomials. All right, so I've told you about these different types of problems: detection, recovery, refutation. I've told you that we're going to think of polynomials as algorithms. But you know, what exactly does it mean for a polynomial to successfully solve one of these problems? All right, so I now want to define this formally. And success, by the way, is always going to be in an asymptotic sense when n is going to infinity. OK, so let's talk about detection first. So what does it mean for a polynomial to successfully solve detection? Well, here's the way I want to define it. We'll call this property strongly separating. Maybe I'll just stop trying to use this. Strongly separating, meaning that, you know, you have your distribution Q. If I feed that to my polynomial, I get some distribution of real numbers as the output. I have my distribution P, feed that to my polynomial, I get a different distribution of outputs. And I want these two to be kind of separated so I could threshold them in the middle. Specifically, I'm going to require them to be separated kind of in terms of the first two moments. So what it's saying here is that the standard deviation of each one is smaller in order than the difference between their means. Right? For recovery problems, we're going to imagine thinking there's some scalar value we want to estimate. So for planted clique, this will be the small x. So let's say small x is going to be the indicator that vertex 1 is in the clique. There's nothing special about vertex 1. You know, if I can estimate vertex 1, I can easily, just as easily do any vertex. And so the notion of success will just be mean squared error. You know, how close can a polynomial f of a being the adjacency matrix, f of a be to x, measured in mean squared error. And then for refutation, there's a similar kind of notion, which again is some kind of strong separation now between a distribution and the property I'm trying to refute. So this R sub k is going to represent the property that there exists a k clique. And you know, here's what the sense in which I'm going to think about polynomials refuting something. Well, the polynomial needs to have these two properties. If there actually is a k clique, it needs to always output a value bigger than 1. Or in other words, if it gives you a value smaller than 1, you know you've successfully refuted a clique. And this second moment condition makes it so that when you give it a random graph, it will actually output something smaller than 1 with high probability. So just to emphasize, these are natural sufficient conditions. I'm saying that if the polynomial had one of these properties, it lets you solve the associated problem. So if you have strong separation, it lets you do detection just by Chebyshev inequality. I'm not claiming necessarily it's the converse, but these are somehow natural conditions based on the first two moments that you can impose. And just as an aside, there's a whole separate line of work on random optimization problems. So this is a separate type of problem where there's not a planted structure. I just give you a totally random graph, and you have to find the largest clique that you can find, and there will be many good solutions out there kind of by chance. So there's a whole separate line of work on low-degree algorithms for this, but I won't try to get into that. Questions so far about this framework?
Do you want a laser pointer? Because I actually have a laser pointer.
Oh, yeah, that would be great.
Fine. Make sure.
OK, let's see. Oh, yeah, good. Thanks. OK, I'll do a double-handed thing. OK, so just to illustrate, here's sort of a prototypical result. Here's the type of thing we might want to prove about a given problem. So this will be the example of planted clique. So this is sort of the main type of thing we try to prove in this area, which is a low-degree lower bound, meaning we're basically proving that in this conjectured hard regime, so the size of the clique is smaller than root n, no matter what low-degree polynomial you take, up to some degree, a little larger than root n, log n, that low-degree polynomials fail at detection, fail at recovery, fail at refutation, in the sense that I defined on the previous slide. And then to complement, and so when we do prove this type of thing, we take this as some kind of concrete evidence, perhaps, of why the problem is inherently hard, or at least we've shown, managed to rule out certain approaches like spectral methods and so on, showing us maybe that this threshold is inherent, at least for certain known classes of algorithms. And we also like to try to complement this with a matching upper bound, to show that this is sharp, and also as sort of a sanity check to make sure that low-degree polynomials can actually recover the best known algorithmic results in the easy regime. OK, so what will I try to talk about today? So some things I don't really want to focus on are kind of, there's this sort of heuristic claim floating around that if polynomials fail, this gives us some kind of evidence for hardness. There's quite a lot of different nuances to discuss here, and if we get into it, we'll be here all day. Also, quite a lot to say about how exactly this relates to other restricted models of computation, like sum of squares and so on. And I also won't focus on too many specific results. But there's a lot to say about all these things, and feel free to ask me about it later. But the thing I mainly want to focus on for the talk is like the proof ideas. So how to actually prove this? How do you actually prove that no low-degree polynomial can solve a given problem? OK, good so far? So, all right, so here's how we start, is usually by, so I've talked about these three different types of problems, the detection, recovery, refutation. I want to kind of reformulate them all in a way so that they all kind of look the same. And so that, starting from maybe the next slide or something, I won't have to treat them all differently. I'll just have kind of one common objective that covers all these things. OK, so let's talk about detection first. So there's kind of a simple reformulation. The proof is not difficult, but I won't go through it now. That if you want to rule out this strong separation, right, you want to show that no polynomial can separate the p and the q, it suffices to bound this certain quantity. This quantity has a few different names. You can think of it as a low-degree analog of the chi-squared divergence. So this is kind of a low-degree analog of some fact from classical statistics. Also called the norm of the low-degree likelihood ratio, although I won't tell you what exactly norm means and so on at this point. The way I want to really define it is by this kind of operational definition here. I'm looking at maximum over polynomials because I want the best one, and I want it to have a large mean under one distribution as compared to its fluctuations under the other. So hopefully it's like kind of intuitive why this should be related to the notion of distinguishing these two. And this is sort of an aside, but in some cases, we actually need to do the analog of a conditional second moment method. So instead of using the original distribution p, you have to take some p prime, which takes some rare bad event and conditions away from that. So it turns out if you establish this for some p prime, it also lets you rule out strong separation. So there's kind of a low degree analog of this conditional second moment method. OK, moving on to recovery. Luckily, we can pose it in kind of a similar way. If we want to show that no polynomial can have a good mean squared error, it suffices also to prove some kind of upper bound on a ratio like this. But now we are saying, now maximizing over polynomials of how much does it correlate with the true thing we're trying to recover, appropriately normalized with respect to its fluctuations, right? These things are all set up so that if I multiply my polynomial by 1,000,000, I don't gain anything. OK, and then finally for refutation, if I want to rule out refutation, it turns out it suffices to construct a planted distribution. That is a distribution supported on graphs with a k-clique, and to show sort of basically low degree hardness between my given distribution Q on which I wanted to refute and this new one that I've constructed. OK, and so the point of this slide is basically to say that all of these can sort of be put under one umbrella, that really my goal is going to be to try to control things of this form. And I'll use the term advantage as kind of a generic term for these types of ratios. So it's going to be a maximum over polynomials of something of this sort divided by some kind of second moment. And so you can recover that, say, the two detection and recovery, either set y equals 1 or y equals the thing you want to recover. And this h on the bottom is some distribution, which is either q in this case or p, the same as the top in this case. OK. So let's talk about how to actually do this. Well, the first thing I want to point out is that in some sense, this is just a linear algebra problem, and I can solve it explicitly. So how would I go about trying to solve this? Well, let's just be very explicit about what this f is. So I'm just going to pick some basis for degree d polynomials. Maybe I could pick just the monomial basis, for example. But I'm not going to fix yet what choice it is. And let's imagine expanding our polynomial. Any given polynomial can be expanded in that basis with certain coefficients f hat, right? And the alpha is just whatever is the indexing set for these things. And now once I do that, this advantage thing, I can write this kind of explicitly in terms of the f hat vector, right? The top is something that's linear in the f hat vector, right, where the c vector is defined by some explicit thing that I can compute. And then the bottom, this quadratic form, is some quadratic function of the f hat vector, where again the p matrix has some explicit form. OK, and now using linear algebra, this thing has some exact explicit solution I can write down. And so maybe we're done. Although the p inverse here is going to be the main issue. So even though we can explicitly compute c and p, and c and p you can compute explicitly, the p inverse turns out to be a real technical issue if you want to actually prove something. And so we're not quite done here, at least not in all cases. But there is one sort of special case in which we are essentially done. OK, so this is just recapping the goal so far. We had this explicit formula. So if it turns out that the distribution on the bottom has independent coordinates, for example, gn 1/2, right? So if this is a product measure, Then, well, I can, remember I got to choose any basis I like in which to expand my f in the first place. If I decide to choose an orthonormal basis of polynomials, that is a basis, orthonormal in this sort of sense, then something great happens, which is that P is just the identity matrix by definition. And so this advantage thing just is the norm of the C vector, which is now just a very explicit thing I can compute. The thing is that finding these orthonormal bases of polynomials, this is something we know how to do for IID distributions or for product measures. There's a very systematic way to do it. But we don't really know how to do it for other types of distributions. Yeah, that's a good point. So yeah, orthogonal polynomials do always exist, and you can in principle use Gram-Schmidt to find them. But I think more to the point, the answer will be really gross, and so you wouldn't want to actually try to explicitly find the norm of C if the C is, the C is defined in terms of these H's, and if these H's are so horrible you can't even write them down or do anything, then you're kind of in trouble. Yeah. Okay, so the upshot here is that for this type of situation, where we're doing a detection problem and we're doing some distribution, distinguishing some distribution versus a product measure, that's somehow kind of that case is now sort of solved using this approach. And this was, a discovery first made by various people in the room, and this led to kind of an initial flurry of a bunch of results along this line. So what I want to talk about mainly in this talk is how to go beyond this. So what do you do when this H on the bottom is not a product measure? Can we still prove anything? And this covers at least two kind of important cases. One would be the recovery question. So if I'm talking about planted clique, can you actually find the clique, or can you decide whether vertex 1 is in the clique? Right, remember for there we needed to put P on the top and also P on the bottom. And so that would be H equals P, and so that's not a product distribution, right? It's really a mixture of product measures, because this planted distribution is like the entire choice of like first pick a random clique and then sample a product distribution based on that clique. A second case that falls into this, where H is not a product measure, would be again a distinguishing question, but now distinguishing in a case where neither of the two distributions is a product measure. So for example, can you distinguish, either I'm going to give you a graph with one planted clique, or I'm going to give you a graph with two planted cliques. So this is what we call like planted versus planted testing, and I think Dana will talk about this more in her talk later this week. Okay, so on a technical level, I want to talk about two different approaches to handling this. Okay, the first one we kind of call the Jensen trick, which was joint work with Sleal. And then the second one is a more recent result about the tensor decomposition problem. I want to present these two in kind of a unified framework. And I want to credit John Niles-Weed for pointing out this kind of way to reinterpret the two results in a way that I can kind of present them both at once. So, all right, just some basic setup. What are we going to try to do? Well, if you remember, this was kind of the problematic thing. This was in the denominator. And this thing, another way to think of it is the norm of f, where inner products and norms for functions are defined kind of in this way. So the inner product between two things is kind of expectation. I'm omitting the actual argument of the function here, right? But this is like expectation of a graph A drawn from H of f of A times g of A. Right, and the norm is defined in terms of that. And so you can do all the usual kinds of facts from Hilbert spaces here. So if I have some orthonormal basis of functions, this norm can be kind of expanded in terms of its projections onto all of these basis elements. And even if I have an orthonormal set, so maybe it doesn't span everything, but these functions are orthonormal, I can still use this to get a one-sided bound on the norm. Okay? So yeah, this last inequality is going to be kind of the key that, what we're going to actually use to bound this thing in the end. All right, so more specifically, here's kind of the common blueprint that I'm going to use for the rest of the talk. So, okay, there's kind of a lot here, so I'll go through it slowly. So here's the proof idea. So let's take, for example, that H is this planet-clique distribution. Right, and remember this means that you have this adjacency matrix, and you start out by just taking these IID Bernoulli 1/2 edges, but then you pick the clique vertices, and once you know the clique vertices, you also know the clique edges, and the clique edges get sort of added automatically. So I can write this A as sort of the entry-wise maximum between this clique edge variables and the IID random noise. Okay, so and more generally, I'm imagining taking the input and sort of writing it in terms of the underlying randomness that generated it. And so, my polynomial, my algorithm, it has to be a function of A, right? The algorithm doesn't know the underlying x and z, but as a proof strategy, we can still think of it as a function of the underlying x and z, right? Not all such functions g are achievable as a f of a, but if I give you any f of a, there is a unique corresponding f of x and z, right? Namely this g of xz is just going to be f of x max z. Okay, so we're going to sort of interpret our polynomial really as a function of the underlying randomness. And then, like I alluded to before, we're going to choose some orthonormal set of functions. So these are, they do crucially need to be orthonormal, but it doesn't have to be a full basis. It can just be a set. It doesn't have to span everything. And furthermore, they're allowed to be functions not necessarily of A, but they can be functions of the underlying randomness, like x and z. And then here's the key thing. If you recall, this f norm was in the denominator originally, and we wanted to prove an upper bound on that thing. So to do that, we want to prove a lower bound on the f norm. Right, so I can prove a lower bound on the f norm by saying, well, it's the same as the g norm because g and f are the same, and I use the sort of fact from Hilbert spaces to do this bound. And I'm just going to define the w's to be these coefficients that appear here. Okay? So okay, now we've lower bounded this thing. But in order for this to be useful, we're going to need to relate these w's back to the original decision variables, right? So originally we were maximizing over f, and we were encoding f by these coefficients f hat. So it's going to be important to think about how this w here is related to the original f hat. And if you kind of work it out, it's not so complicated. There's just a very explicit way that this is related in kind of a linear fashion, right? Just from the definition of these things. So the w is always going to be some particular matrix times the f hats, right? So it's a linear map, and the m I can even write down explicitly, although you don't have to worry so much about the exact equation. Okay, good so far. So here's, in some sense, the main thing. In order to make this approach work out, we are going to need to find an explicit left inverse, m plus for the m. Right? By left inverse, I mean it needs to satisfy this thing. And I claim that if we have that, then we're in good shape. And so this last line is telling you why. Right, so just to recap, this was the thing I wanted to compute, and this is just how it's defined. The top part, like I said before, is just something linear in f hat, so we don't need to worry so much about that. It's the bottom that's more problematic for us, right? So this bottom, in other words, is just the norm of f, and I'm plugging in the bound that here that this is related to the w. Okay, so that's how I get here using this w bound. And now to finish this, well, I'm kind of maximizing over f hat of this f hat, but then this w is something that implicitly depends on the f hat, right? So that's kind of a bit of a mess. I really would like to write everything in terms of f hat. So that's what I'm doing here, right? Because remember, w is m times f hat. So that's what I do on the bottom. And on the top, I'm just throwing in this factor of the identity. And okay, why am I doing that? Because that lets me do the final step, which is to, now that this m times f hat is appearing both on the top and bottom, I can kind of do Cauchy-Schwarz on the top and cancel those two out. And so that's how I get the final result. So the upshot is that, by doing this, I now get some explicit formula I can compute at the end of the day, depending on C, which is something that has a very explicit form. As long as I can compute moments of my distribution, I can do that. And also this m plus this left inverse that I need. Okay, questions?
Sorry, can we go back to the C is defined in terms of the H alphas, and the M relates to M alphas and the T gammas. Is that correct or no?
Yeah, let me see if I can find that. So here it is.
Okay. So you have to select both H and T's, and then you apply this method.
Yeah, that's good. There's two different things you have to choose. You first choose some basis H in which you're going to represent your original polynomial. And those have to be polynomials that are actually of the observed A. And then the T's are more like a proof device. These are some orthonormal set of functions which may depend on the underlying randomness. Yeah, and so eventually we have to choose both of those. Okay, so that's.
Why is it important that here G is a function of X and Z, but not a function of A? Because it seems like everything still holds if you just took another orthonormal basis, T gamma.
Yeah, good. So yeah, G, it would be fine if G were a function of A. What I'm actually doing here is giving you more flexibility to prove it. You're allowed, I'm giving you the flexibility to, if you want, pick a basis that depends on the underlying stuff. So we'll see in a second that this will be convenient for the proof in some cases. But yeah, you're also welcome to pick a basis that only depends on A. Although this may be harder to actually construct such a basis if A is kind of a weird distribution, right? Like if, maybe it'll be more concrete in a second. Good, other questions? Yeah?
Using the quality sign there for the normal set of functions is because you should know the basis? Or?
Yeah, that's right. So when I say orthonormal set, I'm saying, yeah, it doesn't have to span everything. It can if you want, but yeah, I'm trying to do like a kind of generic blueprint to give the prover as much flexibility as possible. Of course, the bound you get at the end of the day, you're not guaranteed to get a good bound, so you probably want to pick as many functions as you can here, and so on. Okay. So let me now maybe try to talk through how to actually apply this to Planet-Clique now. So H is the Planet-Clique distribution. This is just recapping from before. Okay, so I need to start telling you like what actual basis of functions and so on I'm going to use. So okay, one thing to know, I'm going to use these kind of standard Fourier characters. So if alpha is a subset of edges, the associated Fourier character is this thing. So it's kind of a plus minus 1 valued parity function that counts the parity of the number of edges that appear in that subset alpha. Okay, so when you do kind of Boolean Fourier analysis, this is like the standard basis that's often used. And the reason it's used a lot is because these are orthonormal. This is an orthonormal basis of polynomials if your inputs are just IID Bernoulli 1/2. Okay, so if I apply these Fourier characters to the z's, I have an orthonormal basis. If I plug in a, right, a is some more complicated thing. It's not necessarily orthonormal. And so, like we said before, to make this strategy work, I need to pick a basis in which to expand my original f. And so let's just pick, let's just use the Fourier characters applied to a. Right, that's the basis for f. These are not orthonormal, but that's okay. That wasn't a requirement. Now the t's are the ones that do have to be orthonormal, but those are allowed to be allowed to be functions of the underlying x and z. And so what I'm going to do is just forget about the x, and as the t's, I'm just going to use all of the Fourier characters for the z part, for the noise. So I highlighted the x here because it's kind of being ignored. Is that okay? So that is some orthonormal set of functions. It doesn't span, it doesn't span all the functions of x and z. It only spans the functions of z. But I can still use that to get kind of a lower bound on this variance, and this bound will turn out to be good enough. Okay, so that's the choice of the basis. Now, what needs to happen next? Remember, we need to figure out this M matrix. There was this explicit M matrix of how the f hat transfers over to the W, and we needed to try to find an inverse for this, which in general maybe seems like a daunting thing. But luckily in this case, the M turns out to be upper triangular in this sense, and so that lets you find explicitly an inverse for it in kind of a recursive way. So in this case, you actually don't need to use a left inverse. You actually can find just a true inverse. So this M is just a square matrix. Okay, and so the result you get is now this formula from the previous slide. Is this okay? So that's, in a nutshell, that's how this method is applied to planted clique and various other problems of a similar nature, things like planted dense subgraphs and so on. I want to do one more example, which is maybe a slightly different type of problem. So this is a tensor decomposition problem. So how to define this? I'm going to give you an n by n by n tensor, and it's going to have this form. So it's kind of a rank R tensor. So this is, I first pick these random vectors that are plus minus 1. And then I form the rank 1 tensor for each of those vectors, and then I add them all up. But with this slight caveat that the very first one, I'm going to put a bigger norm on that. And that's because I'm going to ask the algorithm to recover that first component. So the larger norm is just sort of for symmetry breaking purposes, because otherwise the algorithm would have no way of knowing which components it's going to try to recover. Okay? And so the goal is to recover A11. That is the first coordinate of the first component vector. Yeah?
If they're all like plus or minus 1, could you do some like nonsense where if like delta is like, should we say, is delta an integer here or is delta?
Yeah, this is a great point. Yeah, you're absolutely right that if delta is not an integer, you can do some weird nonsense to solve this. If you care about polynomial time algorithms. But yeah, it turns out not to matter for low degree polynomials, actually. The low degree polynomials are not able to implement that kind of nonsense, it turns out. But yeah, this gets back to these kind of philosophical questions of, if low degree polynomials fail, do we really believe it's hard? Well, we kind of only believe this if there's a little bit of noise in the problem to begin with, and okay, I'm not going to try to get too much into that. But yeah, this is maybe an example of this is an important issue to point out. Good. Okay, so what do we know about this? So I'm about out of time. What do we know about this problem? When the rank is small enough, smaller than this n to the 3/2, there's polytime algorithms for doing this by some people in this room. And the corresponding low degree lower bound is saying that basically low degree polynomials can solve this, precisely matching this best known algorithm. So when the rank is smaller than this threshold, low degree polynomials succeed, otherwise they fail. Giving some evidence that this thing is kind of really the inherent threshold. All right, so this is a recovery problem. So we're doing mean squared error, or in other words, it suffices to bound some kind of ratio like this, where we're thinking about how much can a polynomial correlate with the thing we want to recover, suitably normalized. Okay, and the way we do this is following the same kind of blueprint as before, with some minor modifications. So here's the model, where again, the algorithm is a function of the tensor T. So it's a polynomial whose inputs are all those entries of my input tensor. But I can sort of also think of it as a function of the underlying A's, right? The A's, these vectors are kind of the underlying randomness. And so, okay, the basis in which to represent f is not so important. Just pick the monomial basis or something. What's more important is we need to find some orthogonal, orthonormal set of functions that are allowed to depend on the underlying A's. And so that's actually easy because the A's are just IID plus minus ones, right? So we can use the orthonormal basis for those, the usual Fourier characters. All right, and so that's roughly how this proof goes. In this case, we really need to use a left inverse rather than a true inverse because the matrix M is actually rectangular. Like there's more, the number of H's and number of T's is not the same, although I forget at the moment which is larger. But you really need to use some kind of a left inverse. But luckily, you have some freedom to choose this left inverse. Like there's actually many left inverses. And so you just have to kind of find a convenient one that works. And so, okay, maybe in the interest of time, I won't try to say too much more about that, but there's some kind of recursive construction. Okay, so just to wrap up, I tried to give you some kind of general blueprint for how we can prove these types of low degree lower bounds, particularly when you're not just testing against an IID or a product measure. Those are not the only tools. A couple that I didn't mention is with Andrea Montanari, we have kind of this very sharp result for getting the exact mean squared error in the spiked Wigner model, although only for constant degree polynomials, and this involves some kind of connection with the approximate message passing algorithms. There's also some work with some people in the room where you can connect these sort of low degree chi-squared or low degree likelihood ratio to some kinds of other objects that, depending if you're a statistical physicist, you might think of this as some kind of annealed Franz Parisi potential, or if you're a statistician, you might think of it as like a classical chi-squared calculation, but where you only have to look at terms where the two replicas have low overlap, if this means anything. And just one open, there's plenty of open questions in this area, I think, about sharpening certain things in terms of the trade-off between degree and signal to noise and all these kinds of things. But one maybe qualitative question that I think is quite wide open is, well, the methods I give you today, we were exploiting a lot of some kind of underlying independence. So the underlying the model, you have a bunch of independent random variables. And so what if you have something like a random regular graph, say like a stochastic block model and a regular graph? Here you don't really have these underlying independent random variables. And so I really have no idea what to do in that case. All right, I'll stop there. Thanks a lot for your attention.